Hello guys, welcome to the physics book. Today we are going to see the chapter heat and calorimetry in class 10 physics. So before going to this chapter, we need to understand few prerequisites to understand this concept of heat, of which law of conservation of energy is the most important thing. So first, before going to understand the law of conservation of energy, let's know what is law of conservation of energy. So law of conservation of energy states that energy in this universe can neither be created nor be destroyed, which means if you have a part of energy, for example, X kilojoules of energy, it cannot be destroyed, and the same X kilojoule of energy you cannot create as well. So it can be transformed from one form to another. For example, you can convert the light energy into electrical energy, electrical into light energy. So on, you can convert between energies, but you cannot create and you cannot destroy. So we can take some simple examples to understand like how the law of conservation of energy works in this universe. So first example, let's take our sun, the star in our solar system. So we all know that, particularly in summer, we all know that sun is giving out radiations which is in the form of heat and light. So where does this heat and light goes? It goes in all the directions of the sun. It's not just only this direction, it goes in all the direction. But for simplicity, let's take the direction of Earth. And after Earth, we will have other planets as well. Let's take Saturn. So these radiations will go like this. So now let's assume that Earth is taking X kilojoules of heat and light. This is heat and light from the sun. Now you should ask me a question, where this X kilojoule of heat is coming from. Obviously, no, it's coming from sun because it's the rays that is coming from sun. But how is sun getting this X kilojoule of energy, heat and light energy? Because as per law of conservation of energy, this X kilojoules cannot be created automatically. So it should be coming from some different forms of energy. So to understand that, let's go inside sun. So sun is having hydrogen atom at the surface. So this hydrogen atom is getting converted into helium. So in this process is called fusion, nuclear fusion. And this nuclear fusion of hydrogen atom to helium atom releases enormous amount of energy in the form of heat and light. Okay, and if you correlate the numbers, right, this will be the X kilojoule of energy. So from this you can understand this X kilojoule of heat and light energy that is reaching Earth and all the others that is surrounding the sun is not created automatically. Rather, it is created within the sun. It's not created, it is converted from nuclear fusion. So now again you will have one more question. Where this X kilojoule of heat and light or fusion energy is coming from? So that is a more conceptual in terms of gravitational energy. We will not touch that. So now you can understand this X kilojoule of heat is reaching Earth. For simplicity, let's take only Earth. Let's not go into Saturn. So now we know that the X kilojoule of heat and light energy is not created. It's coming from a different form of energy. Now what happens to this X kilojoule of heat and light? Will it destroy? As per law of conservation of energy, this X kilojoule of heat and light energy can also be not destroyed. It should be transformed from a different form of energy. For example, let's take Earth. We are having a power grid here. This is nothing but a solar panel. Okay. So when the light of X kilojoule hits this solar panel, the solar panel converts this into electrical energy. Okay. So now we understand that the energy can neither be destroyed nor be created as well. So whatever energy we have, it can be transformed to a different form of energy, or it can be transformed to a different way the energy is exposed to. For example, like heat energy can also be converted into another form of heat energy. But the energy can neither be created nor be destroyed. This is the most important concept of the heat and law of conservation of energy. And we can go to another example, a simple example which we see in day-to-day life. The second example is most simple example, and it's very much essential to understand this example to understand the heat and calorimetry for ICSE physics, which involves an ice cube, a simple ice cube. Let's consider this ice cube is kept in a plate. This is nothing but ice comprising of H2O water, and we all know ice is at 0 degrees Celsius. Okay, now we are having a room. So this ice is kept inside a room. 0 degree ice is kept inside a room. And let's take, like, after 1 hour we are coming to see this ice. What happens to this ice? You all know that this ice will disappear. And what will happen in the plate? We will have water. So what is happening during this transition? Ice is getting converted into water. So what is happening at that time? So what is happening is, room which is at a higher temperature is releasing heat into ice. Heat energy. So the room is releasing heat energy to ice, and the same way this which was ice before is taking in that heat. This is absorbing the heat. For example, if this room is giving out X kilojoule of heat energy, and this ice which was ice and is now converted into water will take this Y kilojoule of heat energy and then get converted into water. So now again, as per law of conservation of energy, there is no energy creations here, or not, and there is no energy destruction as well. So whatever this is giving, this is taking it. So this is the simple example of law of conservation of energy, and this is very key that we will be using this to solve so many problems in the next lectures. And the second most important prerequisites that we need to understand before going into the chapter is, what is a system, what is a surrounding, and what is a universe. Universe here is maybe analogous to what we know as the universe, which involves solar system, constellations, those things, but this universe is somewhat different. So now the same example which we took previously, which is the ice kept in a room. Okay, so in this case, the test subject that we kept, this is called system. Okay, and the room which is like giving the heat energy to ice is called surroundings. As the name says, the system is surrounded by room, so it is a surrounding for this system. So this is a relative term. So if ice is the system in this case, then room will become the surroundings. So putting together, considering both, this is called the universe. So why I need to know that this is a system, this is a surrounding, and combining these two becomes universe? Why I need to know this? This is because we need to understand these, the first prerequisite and the second prerequisite, the law of conservation of energy, and the second point is very much connected. So you will have a doubt here, whether this universe and the universe that we live in, which is like nothing but the solar system, galaxy, nebulae, whether that this universe and that universe is same. Now let's go with an analogy. So universe is equal to system plus surroundings. This is what we have discussed so far. Now the questions that we will have is whether this universe is same as the universe that we live in. So let's consider this as the universe that we live in, which might be equal to galaxies, globular clusters, nebulae, black holes, and so on. So which means this universe can also be categorized as a system plus surroundings. But which is system and which is surrounding depends on us, like what we need to study. Say for example, if you want to study about galaxies, that becomes your system and rest all becomes the surroundings. So which means, like, in a nutshell, this universe and the universe that we are going to that we are living in, both are same. We can constitute this equation for that universe that we live in as well. So the most important thing now that we need to discuss to solve problem is like how the energy interaction in this universe against the system and surroundings will work. So as per law of conservation of energy, energy in this universe is constant. Energy of universe is equal to constant. So let's take this system for an example. So let's take we are keeping this ice at 10 a.m. in the morning in this room. So ice is our system and we are exposing that to the surrounding, which is the room, and this is our universe, taking both the room and the ice. So now what will happen? Energy of universe at 10 a.m. is equal to energy of ice 10 a.m. plus energy of room at 10 a.m. Now we are leaving this ice for 2 hours. Now it becomes 12 p.m. noon. As per law of conservation of energy, this becomes same. This is nothing but whatever was there at 10 a.m. will still be equal to 12 p.m. So this and this are equal. But the right side is not equal. Energy of ice at, ideally speaking, here now it will become water. So we will make this as water at 12 p.m. plus energy of room at 12 p.m. Let me just drop this. So now I just want to equate the first equation and second equation. Because as per law of conservation of energy, we know that energy of universe at 10 a.m. and energy of universe at 12 p.m. both going to be same. So now I am just equating this and this, which means, let me rub this also to make it more clear. So energy of ice at 10 a.m. plus energy of room at 10 a.m. the total should be equal to, let me write it in a different color, energy of water at 12 p.m. plus energy of room at 12 p.m. Now what I'm doing is energy of room at this and this I'm taking in one shot, and this I'm taking to the other side. So what will happen now is energy of room at 11 a.m. minus energy of room at 12 p.m. will be equal to energy of water at 12 p.m. at 12 p.m. minus energy of water at energy of ice at 10 a.m. Okay, so this is the equation. So now if you just simplify this equation, right? Let me rub this diagram. So now I'm just simplifying that equation, which I'm representing this as delta energy of system is equal to delta energy of surroundings. So in this case, the system is nothing but the ice, and in this case, the surrounding is nothing but the room. So this equation states that whatever the system is, whether it is releasing heat or whether it is gaining heat, say for example, if it is releasing heat, the same amount of energy what it is releasing will be gained by the surroundings. Similarly, if it is gaining heat, the same amount of energy should be released from the surroundings. So this equation is the law of conservation of energy. So what is the principle behind this law of conservation of energy is energy of universe is a constant. This is very, very important. And this equation 1, this is equation 2. These two are very key in solving the problems. So you need to note down this too. Now we are into the actual topic. What is heat? The name might be a little bit confusing. The name might be looking as like simple heat, but the actual meaning of what heat means, it is heat transfer or heat in motion, which means like it should always be between two systems or one system and surroundings. Either it can be between system to another system, or it can be between system and surrounding. So now we can take an example to understand this. What is happening within this heat? What does heat means? So let's take a simple example. Let's take our morning coffee. So this is our morning coffee. We are having in a plate. So our mom is giving us a cup of coffee, and let's assume that you are taking this coffee after half an hour. After your mom gave you this coffee, you are taking it after half an hour. So what will happen to this coffee? This coffee will become cold. So why this coffee becomes cold? Because it is losing its heat to surroundings. So surroundings in this case is nothing but the room. Say for example, if I am having a cup of coffee here and I am holding it for 1 hour, within 1 hour the coffee will become very cold because it is losing heat to the surroundings with this just the room. The air in the room will get heated up, but it will be very feeble in such a way that you cannot sense that heat even. So that is what the heat actually means. So now it might be a little bit confusing for you to understand heat. Now we will go to what is temperature and then comes back to what heat is, so that we will understand the difference. So the fourth prerequisite is the understanding temperature. Third one we will come back again, but fourth one is temperature. So this is very, very critical to understand what temperature is and how it is different from the heat. So let's take an example. Water molecule. Let's take a bucket of water. Okay, let me draw a bucket in a different way. This is a bucket which is containing water. Okay, and this is at 70 degrees Celsius. So how I am knowing this is at 70 degrees Celsius is I will put a thermometer inside this, and this will tell me this is at 70 degrees Celsius. Okay. So now what? Okay, we know that the thermometer is measuring this water is at 70 degrees Celsius, but what is this 70 degrees Celsius? That is what the temperature is, and how we can signify this is at 70 degrees Celsius. For that we need to understand the molecular structure of H2O. So let's take H, and in between you will have an oxygen. It's a covalent bond, a single bond here, a single bond here. So this is the hydrogen molecule, this is the water molecule, 2 hydrogen atom and 1 oxygen atom. So now similarly, like we will have almost millions and millions, we don't know how many number of molecules will be there. So let's take N into number of H2O molecules we will have. So what will happen is this H2O molecules will not be at rest in general. So it will go like, it will just do a translation motion like this, it will do a lateral motion like this, and it will also have a rotational motion, like it will twist, it will go like this. So, but a primary difference that we need to note is like, we are putting N here, but the thing is each and every molecule will have its own way of motion. For example, let's take one more molecule here and one more molecule here. So what will happen is, let's assume this is going like this, or maybe let's go at any point in time it is going like this molecule, and this molecule is going down, and this molecule may be rotating. We don't know. It can be in any fashion. It can vibrate, it can move up, the other molecule can move sideways, the other molecule can rotate. So this all can happen within the same bucket of H2. This is happening at the microscopic level. So now, what does this 70 degrees Celsius do here? So we all know that a moving body will always have a kinetic energy. So let's take, this is having some x1 amount of kinetic energy. Coming to this molecule, let's assume that this is having x2 amount of kinetic energy. Coming to this molecule, let's assume x3 amount of kinetic energy. So similarly, we will have so many molecules. Now, the sum of kinetic energy, which is equal to x1 plus x2 plus x3 and so on. And the most important thing is it is directional, which means like if it's going up, it will be positive. If it's going, it is negative. Same way, if it is going this way, it is positive. If it is going this way, it is negative. Similar way, if it is rotating in clockwise, you can take it positive. If it is rotating in anti-clockwise, it is negative. So we need to consider the kinetic energy with sign convention as well. So it can be, when you count this kinetic energy, right, it will be like sum of x, and this kinetic energy is the total energy possessed, total kinetic energy possessed by this bucket of water. And what they will do is, they will divide this by number of molecules of water, number of molecules, H2O molecule. This will give the average kinetic energy of a single molecule of H2O in this bucket. So this average kinetic energy is something this thermometer is measuring, which is the 70 degrees Celsius. So now, with the previous discussion, we get to know that the sum of kinetic energy divided by number of H2O molecule. And please remember that this kinetic energy is directional in nature, which means like you need to consider sign convention, plus or minus. If it's going this way, it's plus. If it's going this way, it's minus. So you need to consider that as well. So if you do this, this is the temperature of this bucket of water. But we don't know like how to count this n number of H2O. We all know that 1 mole, which is Avogadro number, 1 mole of water will contain 6.023 into 10 power 23 molecules. Okay, so now H2O, which is 18 grams in molecular weight. So 18 grams in molecular weight of, if for example, if this H2O is 18 grams, which means it's 1 molecule of water. So this 1 molecule of water in an approximation based on Avogadro's number will contain these many molecules. So we'll get this number. And there are some other ways to measure this kinetic energies as well. Even I'm not sure like how this will be measured, because this is a microscopic measurement. So to generalize this, we cannot keep on like doing this and doing this. So they have invented something called thermometer, which they have standardized like how to measure this 70 degrees Celsius, and the thermometer will do all this activity, calculating this number of molecules, calculating the sum of kinetic energy and doing an average. So this thermometer will do, and this thermometer comes in many ways, like it is mechanical, non-contact, and the chemical. There are many ways of doing these calculations. So that is taken care by the thermometer. As an extension of temperature, we just want to understand one more point. What is meant by hot or what is meant by cold? So if somebody means, let's assume that there is someone who is coming to your house. You are offering him a coffee. So you are asking him whether the coffee is hot or not. The next moment what he says is, you will say that the coffee is hot. Similarly, let's assume the same person is coming the next day. You are giving him a cold drink. And you are asking him whether this cool drink that you have given him is hot or cold. The next moment he will say, cold drink is cold. But is this a correct statement to say whether the coffee is hot, whether the cool drink is cold? If you ask a common person, it is correct. But if you ask an engineer, this is wrong. So why this is wrong? We'll come to that. So means we all know that the cup of coffee is going to be hot, but why in the engineering perspective the coffee saying that the coffee is hot is wrong is because when you say a body as a hot or a cold, you need to have a reference. For example, previously how we discussed this, let's assume this is the system. You should be definitely having a surrounding to define whether this is hot or cold. So in most of the cases in the common life, the coffee will be close to like 70 or 80 degrees Celsius. Let's assume close to the boiling point of water. And the room will be around like 27 degrees Celsius, very less compared to the 80 degrees Celsius. So since the temperature is high at the coffee and not at the room level, so it's a best practice. We will say that the coffee is hot. That is good. But let's assume that somehow the room is at 120 degrees Celsius. It's a hypothetical situation, but still the room is at 120 degrees Celsius. If you ask the same person, allow him to put some thermal masks and all, and let's assume that he is coming into the room and you are offering him a coffee at 80 degrees Celsius. Now, if you ask him the same question, whether the coffee is hot or cold, the next moment he will say that coffee is cold. Because the room is at 120 degrees Celsius, which is your reference and it's a surrounding, and the one that you are determining whether it's hot or cold is the system, and it's at lower temperature compared to the 120 degrees Celsius. When it's at lower temperature, you should specify that as a cold. So, the same case, let's take the cool drink example as well. Let's take cool drink. Let's go with a different color. Oh, my bad. So, let's go with the cool drink. Okay. Now, the same person is coming the next day. You are offering him a cool drink which is at like 12 degrees Celsius and the room is at 27 degrees Celsius. Now obviously this is our system. This is the room, which is nothing but the surroundings. So the person who came to your house who's holding the 12 degrees Celsius cold drink, he will compare that with the 27 degrees Celsius room and he will say that the temperature of the cool drink is lesser compared to the surroundings. So he will say that this is cold. And this is correct. But we are taking that guy who came to your house to Antarctica. There the temperature is minus 16 degrees Celsius. So now you are giving him the cold drink. Ideally it should not be a cold drink, it should be a drink that you are giving. So now what he does is he compares this 12 degrees Celsius cool drink with the surrounding temperature. So now what happens is 12 degrees Celsius is far greater than 16 degrees Celsius. By like 28 degrees Celsius it's greater. So minus 16 degrees Celsius is very low in temperature. 12 degrees Celsius is comparatively higher. So this is not a cold body. This now becomes a hot body. So the same person who told this cold drink as cold when he is at a room temperature, normal temperature, 27 degrees Celsius, he told this as a cold body. When he moves to a different surroundings, which is minus 16 degrees Celsius, will term this cool drink as a hot drink. So this is how hotness or coldness is related. which means you cannot say a specific body. For example, if take a cup of coffee, cake, or candy, or whatever you say, you cannot say that as a hot body or a cold body. You need to compare that with the surrounding to say it's a hot or cold. So that comparison, how will you make? That is where temperature comes into picture. Based on temperature, if it is higher temperature compared to some other surroundings, then it's a hot body. The temperature is lesser compared to surroundings, it means it's a cold body. So this is an important terminology, and you should be intellectual to ask. If somebody is asking you, like, tell whether this is hot or cold, you should ask them with respect to what I need to tell this as a hot or cold body. This is a very good interpretation, like how we need to describe something as hot or cold. Okay, so now, as we promised, like, now we are coming back to what is heat and what is temperature. We need to understand the difference, because it might be misleading that heat is same as the temperature, but it's not. So now coming to heat. What is heat? We already know, like, heat is the energy transferred from one system to another system, or it's between one system or surroundings. It can interact between two. So it is a relative property. That what is relative property? What does it mean? So this is a relative property, which means, like, you can define this property only based on some other system. For example, let's take ice. So you cannot say that this ice is giving X kilojoule of heat. It's not possible, because just ice alone cannot give heat, which will again be opposing the law of conservation of energy. It is destroying X kilojoule of heat, which is not possible. So somebody has to accept this X kilojoules of energy, which is nothing but somewhere room, or you might have a heat exchanger, something should be accepting this X kilojoule, which means ice alone, it's not ice alone cannot characterize this heat property. It needs something else to define this property, which is why this is called a relative property. You can always say that heat is transferred between two objects. Either it can be from one system to another system, or this system to this system. It can be vice versa, or it can be from one system to a surrounding, or surrounding to system. So just taking this system, which was like ice in our case, you cannot define this, because you need another system, which is the room. Or the same case, ice, and you need another system, which is the room. You can consider the room as a system or surrounding. It depends on you, but if you consider this ice and the room both as a system, you need to have one more surrounding, which is like, maybe you can take the other room as well as a surrounding. Let's not go into depth on this. So you can understand this. Heat is a relative property, which will always between two entities. Either it can be between two systems, or it can be between system and surroundings. Coming to temperature. Temperature is a macroscopic property and an absolute property, which means it does not rely on any other entities. For example, let's take this system, only system, the ice. You can simply tell that, okay, ice, this is at 70 degrees, this is at 0 degrees Celsius. You can simply say, only taking ice, only the system. You are not taking any other system, you are not taking any other surroundings like room. Only the ice. It is only one property, only one entity you are taking. So it is an absolute property. With just that particular property, particular entity, we can say that it is at 0 degrees Celsius. It is an absolute property. Then, okay. So I got a question regarding the term macroscopic, because people might think it's a microscopic property, the temperatures, because as we explained in the last part, that we did something like this, going to the atomic level, and it is good to think that it's a microscopic property, but it's not, because if it is microscopic, then we need to consider each and every molecule, how it is behaving. But here, the temperature is nothing but the average kinetic energy. Average kinetic energy of all the molecules present in the bucket of water. So, it's not considering each and every molecule. Going into one molecule, how much is the kinetic energy? Going into the other molecule, how much is the kinetic energy? It's not doing that. It's considering all the molecules, putting together and doing an average. So only the bucket of water is having the property. For each and every molecule, for this molecule, we don't know what the temperature will be. We don't know what the kinetic energy will be. It's combining all the molecules present in that bucket of water. We are doing this temperature. So it is a macroscopic property. If you can find for one molecule H2O, what is the temperature? And what the other molecule H2O, what is the temperature? The other molecule, what is the temperature of the H2O? If you are able to find that, then it becomes a microscopic property. But here it's a macroscopic property because we are doing an average of all the molecules. Okay. How heat is measured? Heat is measured in terms of kilojoules or calories. And is there any way we can directly measure the heat? Not possible. The units in which the heat is measured, it can be kilojoule, it can be calories, or there are many other units. British BU, something is there. Let's not go into that. For our purpose, for our ICSE class 10, we will go with the kilojoules and kilocalories. It can be kilocalories as well. But is there any straightforward way we can directly measure the unit quantity of heat transferred between one system to other system or one system to the surroundings? Not possible. So this is a calculated property. Because this is dependent on various factors, like how much quantity of the substance you are taking, what is the property of that substance, which is specific heat. We'll come to that later. But coming to temperature on the other hand, temperature, as we know, like it can be directly measured with a thermometer. So it is not a calculated property, rather it's an absolute identity, which we already written here. It's an absolute identity directly detected. And there is one more critical part that we need to understand. This is directly detected, this is calculated property. And this heat is dependent on many other factors. The quantity that you are taking. For example, if you are taking 1 bucket of water, the heat transfer will be different. If you are taking 3 buckets of water, the heat transfer will be different. So it depends on how much quantity you are taking of the system or surroundings. So quantity is something very important. Next is the what you are taking. Whether you are taking a bucket of water, whether you are taking a bucket of mercury, whether you are taking a bucket of hydrogen. So it depends on the property of the substance. We'll come to that. What property is this? And here, coming to temperature. Temperature doesn't care about which one you are taking, whether you are taking a bucket of water, whether you are taking a bucket of mercury, whether you're taking a bucket of like alcohol, whatever it is. It does not depend on any characteristics of the substance. It is independent of substance or quantity. It doesn't care like what system you are taking, what surroundings you are taking, whichever, whatever the number is, it's the temperature of that substance or that surroundings. And there is one important concept here. We know that quantity, we know the property of the substance. This third point is something we will use for solving the problems. We will derive this one in some time. And there is one more point which this heat transfer is dependent on, and that is nothing but the temperature. And here it should be intellectual to understand. As I already told, heat can be transferred only between two entities, system to another system or a surrounding. So now the third point, quantity means whether this quantity or this quantity. Property of the substance, this, whether it's the property of this subsystem or this one. Temperature, whether it depends on temperature of this system or this system. So to answer that question, I can say it is dependent on both this and this, both. We will look into that in upcoming lecture. Now we want to discuss one more important topic. This is called internal energy. Whenever somebody is asking you about internal energy, there will be a complication to explain them on heat. Heat is nothing but the heat transfer. And there will be one more complications of enthalpy. So, but this is out of your syllabus, so you can ignore for now. So this is not required. But it's good to know that what enthalpy means. So we will discuss that in a brief way. So what is an internal energy? Okay, let's take the same example. Let's take a block of ice. So this is ice at 0 degrees Celsius. Okay, same way, let's take a cup of coffee. This is at 80 degrees Celsius. Let's take our sun. So now, if you see, let's assume this ice is there and it's not giving out any heat. It's not releasing heat. It's not gaining heat. Nothing is happening. But still, this body is having a temperature, 0 degrees Celsius. And if you convert this into an absolute temperature, which is nothing but 273 Kelvin. Ideally, it is 273.16 Kelvin. And this Kelvin is called absolute temperature. This is absolute temperature measurement. So this we will talk about later. But now let's understand what is internal energy. Whenever this Kelvin is greater than 0, if a body is greater than 0 Kelvin, so it will vibrate. It will do a translatory motion, it will do rotary motions, everything will be happening. So obviously there will be a temperature in that system. So in the ice, though it is looking like a 0 degree Celsius, but in absolute scale it is like a 273.16, which is greater than 0. If any body which is having a greater than 0 Kelvin, it will vibrate. So based on that vibration, it will definitely have a temperature which is 273.16 Kelvin. If any body is having greater than 0 Kelvin, it does possess an internal energy. So all the bodies in the universe will have an internal energy, which is represented by U. So this is not energy in transit. It is like an absolute property. It does not grow from one system to surroundings. Say for example, this is the internal energy. The same ice. It is not the internal energy that we are discussing is not the heat transfer that is going to the room. Rather, it is the heat. It's not actually the correct word heat to say. It is the internal energy which is residing within the ice. Similar way, let's assume coffee. Here also, let's talk about internal energy. Internal energy, it's an absolute property. It's not like the energy interaction that this is the system now doing with the surroundings, the room. It's not that one. Rather, it is an absolute property which is residing within this coffee itself. So the coffee is at 80 degrees Celsius, which means 273.16 plus 80, which is 353.16 Kelvin. So it's greater than 0. Obviously, it will have an internal energy. And this internal energy is coming by virtue of its temperature in Kelvin. So if a body is having a Kelvin, means greater than 0 Kelvin, it does possess an internal energy by virtue of its temperature. It's not an energy transfer between system and surrounding or system between system. It is energy that is possessed within one system. So this is the system. It is energy possessed in the system by virtue of its temperature, and temperature is in Kelvin. Now third case. This is also same case, but the only difference is sun will be like around 5000 degrees Celsius. So this will be 5273.16 Kelvin, And it's the same by virtue of temperature 5000 degrees Celsius or 5273.16 Kelvin, it does possess some internal energy. So now let's go with why we are considering Kelvin. I just want to reiterate what I said. Internal energy is not energy in transit, because when we compare heat or heat transfer, it is between system to another system or surroundings. Only in this context heat transfer happens, and it's a relative term. But on the other hand, internal energy, it will be happening within the system only, and it's by virtue of temperature. This is very, very important, and most of the time internal energy will be called as energy in storage. Because this is like a reservoir of heat. It will store the heat within the body itself by virtue of its temperature. Say for example, the coffee which we saw just now, it's at 80 degrees Celsius. By having 80 degrees Celsius, it is storing some amount of energy within itself. And that energy in storage is called internal energy, and we should not confuse that with heat transfer. Heat transfer is between two different things. This is within one system itself. So now we need to understand, like in some problems we will be having degrees Celsius, and in some problem we will be using Kelvin. But why there is two different scale, and this degree Celsius is something different, but this Kelvin is called absolute temperature. The term absolute temperature here, what it means is this is the actual temperature scale. Why this is said as actual temperature scale and not this one is, or why they came up with this approach of using Kelvin rather than degree Celsius? Why degree Celsius is still prevailing? These are the questions that we are going to answer. The first thing is degree Celsius is easy to use because the number will be reduced, number will be released. Because, for example, if ice is at 0 degrees Celsius, simply you will just describe this as 0 degrees Celsius. But the same way, the same ice at 0 degrees Celsius, it will be like 273.13 Kelvin. The representation becomes very messier. So that's why for simplicity, they are still using degree Celsius, but the correct way to use is Kelvin. If there is any possibility for you to use absolute temperature Kelvin, always go with that Kelvin. The next thing is why they actually found this absolute temperature. What is the significance of this Kelvin over degree Celsius? Let's take a block of ice. This is at 0 degrees Celsius. So you should ask me the question now. You said that molecules will be vibrating, molecules will be rotating, molecules will be translating. So all these movements will be there, which will give you them the kinetic energy, and based on that kinetic energy, they will average it out, and it will have a temperature. Now it looks like 0 degrees Celsius means it doesn't have any kinetic energy. This is where the problem comes in. Now it is giving a bad impression, as in 0 degree block of ice is not having any kinetic energy at all, or the average kinetic energy, which we call as temperature. But in reality, 0 degrees Celsius ice, the water molecules in that ice are actually vibrating. But it's giving a wrong picture that 0 degree ice is not at all vibrating. The H2O molecules in the ice are not at all vibrating. So what they did is, they introduced the absolute temperature scale. So the 0 degrees Celsius, instead of representing like this, they represented like this. Now, if you go, the temperature is equal to 273.16 Kelvin. So now if somebody is seeing this number, they will know, okay, this is greater than 0. So there should be some kinetic energy of the molecules. This is the same block of ice represented in a different scale, but it is giving a correct picture saying that, okay, kinetic energy of molecules are there. So this is the correct representation of how a temperature needs to be represented. On the other hand, let's go minus 273.16 degrees Celsius ice. So what it means? It looks like the direction in which the molecules are vibrating are changed completely because it's in minus sign. So what it looks like is orientation of kinetic energy changes. So that is what it is signifying. When you look at this is like in positive number or it's at least 0, but this is in negative numbers, which will give us an impression that the energy direction is changing. But actually that is not happening. What is happening at this temperature is this is 0 Kelvin. As the number says 0 Kelvin, literally kinetic energy of the molecules is 0, which means the molecules stopped working. This is the ultimate critical point. The universe stops. So when there is some object achieving this temperature, which it will not obey the law of thermodynamics or whatever laws of physics scientists so far found. So it will not obey. So whenever a body is trying to reach this temperature, all the physics stops working. So we will just go with the quick recap of what we saw. Actually, we haven't entered the heat and calorimetry topic itself so far. We have just gone through the prerequisites of what we need to understand before going into the heat and calorimetry chapter. So what we discussed is first is law of conservation of energy, which states that energy can neither be created nor be destroyed. So let me do one thing. So the first law of, the first prerequisite is law of conservation of energy, which states that energy can neither be created nor be destroyed in this universe. So energy of the universe is constant. We derived this equation, and based on this assumption, what we derived is change in energy for a system will always be equal to change in energy of surroundings. So this is the second equation that we derived. These two are very, very, very important. I would say, please make a note of it. This is very, very important in problem solving. So these two equations came out of a result of law of conservation of energy. And next one is like system, surrounding, and universe. What is system, what is surrounding, and what is universe? The one that we are considering for the calculations in terms of examination, the one that we are using for calculations are the system that we are considering. For example, if somebody is talking about to measure the temperature of water, measure the temperature of ice, then that becomes the system. Against what you need to measure is what is the reference point, and that becomes the surrounding. So system is the test subject. So for what you need to find something, for example, what you need to find the heat transfer, what you need to find the specific heat capacity, or for what you need to find the temperature, that becomes a system. With respect to what you need to find answers for this becomes the surroundings. So if I give an example, in our case, we took ice to determine temperature of ice. If you want to determine the quantity of ice that is being used or the temperature of the ice, then that becomes your system. Against what is the room? You are just making the room to give heat to the system. So based on this interaction, you need to find the system's parameter, and the surroundings parameter will be given to you, obviously, because if you know this, then only you can find this. So putting together these two things will form the universe. Universe is not a different terminology. System plus surrounding will constitute you the universe. Don't worry about the problems. We will go to the problems in depth in later classes. So fourth one is, actually this is a third point here, but in here it is coming as 4. So fourth point is heat transfer. What is heat transfer? Actually, the term heat is analogous to heat transfer. So heat transfer is nothing but the energy that is being absorbed or given out from a system to the surroundings, or from the surroundings it's going to the system, or it can be between two systems. So heat is nothing but thermal energy interaction between system and surroundings. And please note that this heat or heat transfer is not energy in storage. This is energy in transit, which is always flow of energy from one system to another, that system to this system, or between surroundings to system. It will be like flow of energy. It's not like energy that is stored in a particular system. Next comes is the temperature. So what is the temperature? Temperature, we all know by this time, is the average kinetic energy of all the molecules present in the system. So what it means, like, so you will be taking all the molecules into consideration, adding up the kinetic energy of all the molecules, and this kinetic energy may be coming from translation motion of the molecule, rotational motion of the molecule, or vibrational motion of the molecule. So you will average out for all the number of molecules present in the system that you are considering. So that will give you the temperature, but we will not do that kind of difficulty in measuring a temperature. Rather, we will use a thermometer to measure the temperature. So next is, we also discussed about the difference between heat and temperature. Heat is an energy which is in transit between two different bodies, like surroundings and system, or system to system. But temperature is an absolute property in a macroscopic scale which is determined. It is, temperature is measured in degrees Celsius, Kelvin, or Fahrenheit, whatever. But heat, it is measured in joules, kilojoules, calories. So units you can. Also, based on temperature, we may say whether a body is hot or cold. But again, temperature, with just temperature, you cannot say whether a body is hot or cold, because you need to refer to a surroundings to say, based on this temperature, whether the system is hot or cold. So temperature, to determine whether body is hot or cold, you can use temperature, but only with the temperature you cannot say. You need to know the temperature of the surroundings as well. So last but not least, we'll end up with this. So we have discussed about the internal energy. Internal energy might be similar to heat energy, but the only difference is internal energy is stored within the system itself, or within the surrounding itself. It is not moving between surrounding to system or system to system. It is by virtue of its temperature. If a body has a temperature greater than 0 Kelvin, it does have an internal energy, and it is in storage. The body is storing that energy within itself by virtue of its temperature. By virtue of its temperature means by having that temperature. So that's it for the next topic. We will be discussing pretty much about thermal equilibrium. Thermal equilibrium, and what is M, what is Cp, what is delta T, which is very, very, very important after the first law derivations that we derived two equations, right? This is the third equations, which is going to be very, very useful for you for the examinations. And then types of heat transfer. And this is not for ICSE, but still it is good for you to know so that you can have more knowledge on what heat transfer really means. And then we will work on heating and cooling process. And another important category which we will be working on is like temperature time curve of heating or cooling. Mostly to arrive this, we will be using water, because as per ICSE 10th syllabus, it is comprising only of water. So we will stick to that. And then again, not but not least, problems. Okay, thank you.